In addition to making sure that we convey the level of precision of our instruments in reporting our data, we will sometimes have calculations to do on that data. In order to convey the precision of the resulting calculation, we will need to use the mathematical concept of significant figures. We will learn the 5 rules for determining how many significant figures are in a number, most of which can be seen in this example number. The trickiest part is determining which zeros in the number are significant and which zeros are not. Our first rule is that all non-zero digits are significant. So if it is any number 1 through 9, it is significant. For example, in the number 112.1, all of the digits are non-zero, so they are all significant. All the rest of our rules deal with zeros. As we look at the rules, we are determining whether the zeros are in the middle, right, or left of some non-zero digits. It does not matter where the zeros are in relation to the decimal point. It only matters where they are in relation to the non-zero digits. Rule number 2 says that zeros between non-zero digits are significant. I like to think of these zeros as being the cream in the middle of the Oreo or the meat in the middle of the sandwich. These zeros are significant because they are sandwiched in between significant digits. For example, in the number 50.08, the zeros in the middle are significant because they are in between the 5 and the 8, which are non-zero digits. Rule number 3 says that zeros to the left of non-zero digits are not significant. These zeros on the left-hand side are just placeholders. They tell the magnitude of the measurement, but not the precision. For example, in 0.0023, the zeros are all to the left of the 2, our first non-zero digit, so they are not significant. Rule number 4 says that when there is a decimal point in the number, zeros to the right of non-zero digits are significant. For example, in the number 1.200, the zeros are after the 2, and there is a decimal point in the number, so the zeros are significant. Again, it doesn't matter where the decimal point is in the number, it just matters that it is in there somewhere. Rule number 5 says that when there is not a decimal point in the number, zeros to the right of non-zero digits are ambiguous. We don't know how many significant figures this type of number has. For example, let's say we have the number 100 with no decimal point. This could have been measured to the ones place, the tens place, or the hundreds place. The number alone does not communicate that without a decimal point. If we wanted to convey that we measured to the ones place, we could put a decimal point in. 100 decimal. That number with the decimal would have 3 significant figures. But how would we report it if we had measured to the tens place? The only way to convey 2 significant figures would be to write it in scientific notation. 1 times 10 to the 2 would be 1 significant figure. 1.0 times 10 to the 2 would be 2 significant figures. 1.00 times 10 to the 2 would be 3 significant figures, and so on. If you take any engineering classes, you may be told that when there is no decimal point, the zeros on the right are considered not significant. Therefore, 100 with no decimal point would be considered to have 1 significant figure. When in doubt, as you read scientific literature, it is your safest bet to assume they are not significant, since you can't tell from the way the number is reported. For the purposes of this class, rather than reporting a number of significant figures, you will just say that this type of number is ambiguous. How many significant figures are in the number 32.800? Is it A, 1, B, 2, C, 3, or D, 5? The correct answer is D, 5. The first 3 digits are significant because they are non-zero, and the last 2 are significant because they are on the right of all the non-zero digits, and there is a decimal point in the number. How many significant figures are in the number 67,400? Is it A, ambiguous, B, 3, C, 4, or D, 5? The correct answer is A, ambiguous. There are zeros on the right of the non-zero digits, and there is no decimal point, so we don't know if they are significant. A number expressed in scientific notation is always written in a particular way. There will always be some number called the coefficient in front, followed by a power of 10. The coefficient will always have one digit, a decimal point, and the rest of the numbers. When a number is written in proper scientific notation, all of the digits in the coefficient will be significant. The power of 10 is just a placeholder that tells us how large or small the number is. The reason the coefficient is always significant is that it always has a non-zero digit followed by a decimal, and then the rest of the numbers. Therefore, there are never zeros to the left of the first non-zero digit, and there is always a decimal, so zeros to the right are always significant. A number written in scientific notation will always have the same number of significant figures as if we had written it in decimal. For example, 0.001307 has 4 significant figures, and 1.307 times 10 to the minus 3 also has 4 significant figures. Please look online or get tutoring if you need a refresher on how to convert numbers from decimal to scientific notation and vice versa. I will assume it is a skill you already have. How many significant figures are in the number 4.300 times 10 to the minus 3? Is it A, 2, B, 3, C, 4, or D, 6? The correct answer is C, 4. All 4 digits in the coefficient are significant. The power of 10 does not affect the significant figures. We could also have written the number as 0.004300, which would also have 4 significant figures. The zeros on the left would not be significant.